7:20 this
Okay, our clock is messed up again. It's not 3 o'clock in the afternoon, but it is 11 o'clock, so it's time for us to start. Hopefully you had a good 3-day weekend. Our first announcement of importance is that we are having a quiz on Friday, our second quiz of the semester. So that quiz will encompass everything up through the end of class today. So make sure you're paying close attention to what we go over today, and make sure that you're on time and ready to start at the beginning of class on Friday. Today we're going to discuss in detail electrophilic aromatic substitution reactions on substituted benzenes. And there's going to be 2 questions we're going to ask and then answer. The first question is the substituent going to make the compound more reactive than benzene or less reactive than benzene? Meaning, will the reaction be faster than the corresponding electrophilic aromatic substitution of benzene, or will it be slower? That's activating or deactivating effects. And then the other question we'll ask is, where is the new substituent going to be on the ring? Is it going to be ortho, meta, or para relative to the original substituent? So, to understand these effects, first we have to determine if our substituent on the benzene ring is an electron donating group or an electron withdrawing group, because that's going to impact these activating and deactivating effects as well as the directing effects. And there are 2 ways that substituents can donate or withdraw electrons, and that is induction as well as resonance. So let's look at those effects separately, and I've drawn a couple of them for you on the board already. If our substituent is an electronegative heteroatom, such as a nitrogen, an oxygen, or a halogen, that atom will be more electronegative than the carbon it is bonded to, and so that carbon heteroatom bond will be polarized towards the heteroatom, withdrawing electrons from the benzene ring. So inductively, our heteroatom substituents are going to be electron withdrawing groups. Then we'll look at alkyl groups. So alkyl groups are capable of donating electrons by hyperconjugation and induction. We have either carbon-hydrogen bonds, carbon-hydrogen sigma bonds in a methyl group. If it's a longer alkyl group, we have some combination of carbon-hydrogen and carbon-carbon bonds. But the electrons in those sigma bonds can be donated by resonance or by by induction or by hyperconjugation, as we learned when we talked about how alkyl groups donate electrons to carbocations. Okay? So alkyl groups are going to be electron donating groups, but this effect is weaker than the effect we see over here. So they're weak electron donating groups by induction. Another way to understand this phenomenon is to recognize that an sp2 carbon is slightly more electronegative than an sp3 carbon. We discussed this when we were learning about alkyl groups stabilizing alkenes by donating electrons to alkenes. We said that the more electronegative sp2 carbon of an alkene is going to attract the electrons from the less electronegative sp3 carbon of an alkyl group. Okay? So 2 ways to understand this, induction as well as the weakly polar bond that we get from an sp2 carbon being more electronegative than an sp3 carbon. Are there any questions on these inductive effects? Okay. So let's look at resonance effects that we can see with different substituents. Okay. And in order for there to be resonance effects, we have to have either pi electrons or lone pairs, so pi bonds or lone pairs on the atom that is attached to the benzene ring. That's the only way we'll be able to have resonance effects. So Let's look at what happens when we have a substituent with lone pairs. A lone pair or lone pairs attached to the benzene ring. So this molecule is aniline. It has an NH2 group attached. That nitrogen has a lone pair. We know that anytime we have a lone pair adjacent to a pi bond, we're able to draw a resonance structure. So that resonance structure would look like this. Okay? And this is a minor contributor because it's not aromatic. It also has formal charges that we didn't have in our original structure. So this is a minor contributor. But nonetheless, it does contribute to the structure of aniline. And we can move that lone pair around the ring. We can delocalize that negative charge, formal negative charge. We can delocalize it on 3 of the carbons in the ring. So we end up with 3 different, forgot an arrow there, sorry. Okay. So again, these are all minor contributors, but as I mentioned in the chapter 16 lectures, minor contributors can provide clues about the reactivity of compounds. And these 3 minor contributors all have a negative charge in the ring. And so that tells us that our ring is going to be electron rich. And so that tells us that by resonance, the NH2 group is donating electrons to the benzene ring. Any questions? Okay. Let's look at a substituent that has a pi bond attached or conjugated to our benzene ring. Okay. We're going to look at nitrobenzene. Okay. Here's the Lewis structure for nitrobenzene. We have a nitrogen-oxygen pi bond. Importantly, in this pi bond, the atom that is not attached to the benzene ring is more electronegative than the atom that is. Oxygen is more electronegative than nitrogen. So this pi bond, both of these bonds are polarized towards the oxygen. So whenever we have a pi bond that is polarized, we can draw a resonance structure where we're pushing the pi electrons onto the more electronegative of those atoms. And then in this case, we can move pi electrons from the benzene ring. Fix that. So we end up with a positive charge in the ring, a carbon-nitrogen double bond. So we have a lot of formal charges in this minor contributor. Okay? And it's a minor contributor because it's not aromatic, but it still does contribute to the structure of nitrobenzene. And we have 2 additional minor contributors that we will draw. Okay? So in the minor contributors of nitrobenzene, we have positive charges in the ring. And so that indicates that the benzene ring of nitrobenzene is electron deficient, has less electron density than the ring of benzene. Okay? So the nitro group is going to withdraw electrons from the benzene ring by resonance. We can draw similar structures with substituents bearing a carbonyl group. If we had an aldehyde or a ketone or an ester, any functional group that had a carbon-oxygen double bond attached to or conjugated to our benzene ring, we could draw similar sorts of resonance structures. And I believe there's an example of that in the book. Okay? So, to understand the overall effects of these substituents, we need to consider both the inductive effects and the resonance effects. Okay? If they're working together, it's going to be easy to conclude if it's a donating group or withdrawing group. If they're working against each other, we're going to have to decide if the inductive effects are greater or the resonance effects are greater. So let's look at our alkyl groups to start. There are no resonance effects with our alkyl groups, only inductive effects. So that's our easiest one to make a decision about. Our alkyl groups are going to be electron donating groups. Okay? They're weakly donating because, as I mentioned, the magnitude of this effect is not particularly strong. Okay? Now let's look at what happens with our electronegative heteroatoms. And we'll start with nitrogen and oxygen. We know that by induction, these electronegative heteroatoms will withdraw electrons from the benzene ring. But over here, we've shown that by resonance, these groups are going to donate electrons to the ring. Okay? So we have to make a decision which of those effects is going to be greater. And it depends on the nature of the heteroatom. If it is a nitrogen or an oxygen, and note this is a nitrogen or an oxygen with at least one lone pair. So we're not talking about the nitro group in this case. Okay? We're talking about amines, alcohols, ethers, these types of compounds. If we look at our periodic table, we see that as far as heteroatoms go, nitrogen and oxygen are not terribly electronegative. They're less electronegative than the halogens. Okay? And so because they're less electronegative than the halogens, that inductive effect, which depends on electronegativity, is not as strong. And the resonance effect is stronger. Okay? So if it is a compound that has a nitrogen or an oxygen with at least one lone pair, that's going to be an electron donating group. Because the resonance effect is going to be stronger than the inductive effect. That resonance donating effect is going to be stronger than the inductive withdrawing effect. Any questions? Okay. Now, let's consider what happens with a halogen. I've drawn fluorine over here on the board. We look at our periodic table. Fluorine and chlorine are very electronegative. And so the magnitude of that inductive effect is going to be stronger than with nitrogen or oxygen. So what happens with fluorine and chlorine, the net result is they are electron withdrawing groups because the magnitude of the inductive effect is stronger than the magnitude of the resonance effect. Okay? So what about, before I write on the board, what about chlorine and bromine? Bromine and iodine. Bromine and iodine are less electronegative than fluorine and chlorine because they're further down the periodic table. So because they're less electronegative, now this inductive effect is going to be weaker. However, the resonance effect is also weaker because as you go down the periodic table, the bond lengths increase. And so as you move the lone pairs on the halogen further away from the benzene ring due to the longer bonds, the resonance effect also becomes weaker. Okay? So with bromine and iodine, you still have a stronger inductive effect than resonance effect. Okay? So with a halogen substituent, that is going to be an electron withdrawing group. The inductive effect is going to be stronger than the resonance effect. Okay, any questions? All right, let's look at our nitro group. And this also applies to our compounds with carbonyl groups attached, aldehydes, ketones, esters. We know that by resonance, they are withdrawing groups. What about induction? So here we have a ketone attached to our benzene ring. This carbon-oxygen double bond is polarized towards the oxygen. So we have a partial negative charge on the carbon, or on the oxygen, a partial positive charge on the carbon. Having a partial positive charge on the atom attached to the benzene ring means that it will withdraw electrons inductively. Okay. And here we see in the nitro group, in our major contributor, we have a formal positive charge on the atom attached to the benzene ring. So anytime we have a formal positive charge or a partial positive charge on the atom attached to the benzene ring, that substituent will withdraw electrons inductively. We've also seen how those substituents can withdraw electrons by resonance. So we know that those substituents with pi bonds, which also end up putting partial positive or formal positive charges on the benzene ring, will be electron withdrawing groups. Questions? Yes?
What does it mean when something is polarizable? Like
Polarizable means that the electron cloud responds to its environment. So if you were to bring an atom with a partial positive charge close in space, then the electrons would adjust. So we end up with temporary dipoles when we have polarizable atoms. Okay? So that didn't really enter a whole lot into our discussion today. I mean, you could say that the polarizability of the electrons in the alkyl group are resulting in this induction, but it didn't really enter into our discussion a whole lot of these substituents and their effects. So here we have a figure showing us electrostatic potential maps of aniline, benzene, and benzaldehyde. If we compare each of these to benzene, with aniline we see that the red is a bit more intense, and there's some red on the nitrogen. That's indicative of that amine donating electrons to the aromatic ring. And then over here with benzaldehyde, we see the ring is green, and the red is up on the oxygen. That's reflective of the substituent, the carbonyl group in this case, withdrawing electrons from the benzene ring. Okay? All right, so any questions on how we decide whether a substituent is an electron withdrawing group or an electron donating group? There's a nice summary from the book showing this to you. Donating groups, alkyl groups, or groups that have a nitrogen or an oxygen with a lone pair. Withdrawing groups have a halogen, or they have an atom with a positive or partial positive charge on the benzene ring, which usually is part of a double bond. Okay? All right, so now we need to apply this knowledge to electrophilic aromatic substitutions. And there are going to be two issues here. One is the rate of the reaction. Is it going to be faster or slower than the reaction with benzene itself? And then the second question is going to be the orientation of the product. Is the new substituent going to be at the ortho position, the meta position, or the para position relative to the original substituent? So let's look at a couple of examples, and then we'll explain them. So first, we're going to perform the bromination of toluene. Toluene has a methyl group. We know that that's a weak electron donating group. We're going to brominate. And I'm going to draw the three possible products. And then I'm going to give you the ratios of those products that are obtained. This is the meta. And this is the para. And so what we find in the bromination of toluene is we get about 40% of the ortho product, about 60% of the para product, and hardly any of the meta product, somewhere between 0 and 1% of the meta product. Okay? And when we measure the rate of the reaction, we find that the bromination of toluene is faster than the bromination of benzene. Okay? So we would say that the methyl group is an activator, meaning it makes the ring react faster than benzene itself, and it is an ortho-para director. And this is common. Whenever you see ortho products, you typically also see para products, and you usually see them in close to a 1-to-1 ratio. There are 2 ortho positions relative to the para position, so you might expect a 2-to-1 ratio of those products statistically. However, the ortho positions are more sterically hindered because they are adjacent to the existing substituent. So that slows down attack at the ortho positions relative to the para position. So the result is you typically get pretty close to a 1-to-1 mixture. You can skew these ratios if you change the size of that group. If it's a tert-butyl group, you're going to get a lot more para than what we see here. Okay? Any questions on this particular example? Yes?
You said you called it a para director?
Yes, an ortho-para director. Okay? So the methyl group is an activator and an ortho-para director. All right, let's look at nitrobenzene. And in this case, we're going to install a second nitro group with nitric and sulfuric acid. So we're going to make dinitrobenzene. And we've got the 3 possibilities, ortho, meta, and para. And in this case, we end up with mostly the meta. We get 93% of meta. We get about 7% of ortho, and somewhere between 0 to 1% of para. Why we get more ortho than para, I do not know. But the take-home message here is that meta is by far the major product when we're performing electrophilic aromatic substitution on nitrobenzene. This reaction is going to be much slower than the nitration of benzene itself. So we would say that the nitro group is a deactivator. It slows down electrophilic aromatic substitution. And it is a meta director. Okay? So there are 3 types of substituents, 3 categories of substituents. We have substituents that are activators, and they are ortho-para directors. Okay? Any substituent that directs the substitution to the ortho position will also direct it to the para position. Okay? Alkyl groups will be in this category. We saw that here with toluene. And heteroatoms, we'll say Z. This is going to be either nitrogens or oxygens that have at least one lone pair. Okay? So not the nitro group, but alcohols, ethers, amines. We'll show you a list of them later on in a table. But this Z refers to oxygen or nitrogen with at least one lone pair. I suppose you could throw sulfur in there as well. Our second category of substituents are going to be deactivators that are also ortho and para directors. Okay? And these are going to be the halogens. They're deactivators because of the electronegativity. We talked about how the inductive effect is stronger than the resonance effect with halogens. And later on, we're going to learn why they are ortho-para directors. Okay? And then our third category of substituents are going to be the deactivators that are meta-directors. Okay? From our example, we've seen that the nitro group fits in this category. So these are going to be the substituents that have a formal positive or a partial positive charge on the atom attached to the aromatic ring. Okay? So that would be the nitro group, that would be any carbonyl-based functional group that would fit in this particular category. Okay? All right, so we see that there's only one type of activator. All activators will be ortho-para directors. And then we see that our deactivators can either be ortho-para or meta. Okay? So let's look at a sample problem here. This is actually two sample problems rolled into one. We're supposed to predict the product or products, and then we're supposed to decide if we get if the reaction is faster than the reaction with benzene or slower than the reaction with benzene. Okay? So our first example, this is an amide. It's an amide that has the nitrogen attached to the benzene ring. There's a lone pair on that nitrogen. So that lone pair makes this an activator and an ortho-para director. So we get the ortho and para products. We usually don't ask you to predict a ratio. We usually just ask you to conclude that ortho and para will be the major products. And this compound will react faster than benzene itself in the nitration. Okay. Second example, we have an ester attached to our benzene ring, and we're performing a bromination. We have a partial positive charge on the carbonyl carbon. That makes this group a deactivator and a meta-director. So we get one major product, and this reaction will proceed more slowly than the bromination of benzene itself. Okay? Any questions about these sample problems? Okay, yes?
Just to clarify real quick, activators means that the reaction will be faster than for normal benzene and deactivators are slower?
Yes. Yes, activators will make the reaction faster than benzene. Deactivators will make the reaction slower than benzene. So we're going to explain the activating and deactivating effects in a moment. Before we do that, let's get out our eye clickers. We have an eye clicker question. So here we are performing a Friedel-Crafts acylation on ethylbenzene. So go ahead and talk to your neighbors and decide which of these products or products is going to be the major from this reaction. Okay? And the ET here is just referring to the ethyl group in that starting material. What do you think the transfer I'm thinking it would be so this reaction is from not too hard, right? The group which makes it carbocation. I just don't remember the and it would stay on the carbon acid. Oh, wait, no, would it? I don't know. Let's try to get our final answers in the next 15 or 20 seconds.
So it's looking like it's going to have that carbocation right on the carbon there, which would put it into the deactivator and metaderivator.
Okay. Oh, there's another answer. Wait. Any more answers coming in? So once, 29.
Yeah.
More. Okay, we'll go ahead and stop this. All right. So which product or products would we expect? Anyone? Yeah, I heard 1 and 3 from the front here. Grady, why?
Because the ethyl is an alkyl group, so it's electron donating. So
Okay.
it's an activator of an ortho-para director.
That's right. This is an alkyl group. It activates the ring. And so it is an ortho-para director, just like the example we had here with toluene. And so that tells us we will get 1 and 3. Now our ketone that we installed is a deactivator, but that doesn't matter. That's the new group that we installed. We're looking at the substituent that was there in the first place. That's an activator and an ortho-para director. So 1 and 3 will be the major products. Any questions? All right, so let's look briefly at a table. This is a table here of our substituents and their directing and activating effects. So everything above the solid line is an activating group. Everything below the solid line is a deactivating group. All of our activators are ortho-para directors. Our deactivators are divided into 2 groups: the meta-directors, the ones that have the positive or partial positive charge on an atom attached to the ring, and our halogens. Our halogens are unique. They are deactivators because they're net electron withdrawing groups, but they are ortho-para directors. And as we'll see in a moment, that's due to the fact that they have lone pairs. Okay? So they're deactivators with lone pairs, which makes them ortho-para directors. The deactivators that don't have lone pairs on the atom attached to the ring are meta-directors. We need to understand the why behind activating or deactivating and directing effects. And let's talk about the activating and deactivating effects first. Okay? So we've established that if we have an electron donating group attached to our benzene ring, then that compound will react faster than benzene. Whereas if we have an electron withdrawing group, that compound will react slower than benzene. Why? Who would like to raise their hand and explain why that is the case? Okay, go ahead.
Is it because the additional electrons from the resonance effect are more reactive with the electrophile?
Okay, so the benzene ring in an electrophilic aromatic substitution is functioning as our nucleophile. So it stands to reason that if we add electrons to the benzene ring, it will be more nucleophilic and more reactive. And that's correct. When we talk about reaction rates, we need to focus on the rate determining step of the reaction. What is the rate determining step of every electrophilic aromatic substitution? They all have the same rate determining step. Yeah?
Forming a carbocation.
Formation of the carbocation. We have attack of the pi electrons on the electrophile, generating a carbocation. Carbocations always form slowly. In this case, we lose aromaticity to do so. So definitely, that's our rate determining step. Is that first step of the electrophilic aromatic substitution endothermic or exothermic? Is that carbocation intermediate higher in energy or lower in energy than our starting aromatic compound? It's much higher, so that's going to be endothermic. What does Hammond's postulate tell us about endothermic reaction steps? You can raise your hand and tell us what Hammond's postulate tells us. Grace? Okay. So we know that the transition state of an endothermic step is going to more closely resemble the product of that step than the reactants. Okay? So the transition state of the rate determining step will look an awful lot like that carbocation. Okay? Because of that, we can conclude that more stable carbocations will be formed faster. Because if we're comparing 2 processes, The one that forms the more stable carbocation will have a lower energy transition state and therefore have a lower activation energy and occur faster. Okay? So these are principles based on Hammond's postulate that we need to remember from last semester. So we can look at these diagrams here, and we can see three of these rate determining steps of electrophilic aromatic substitutions. We got benzene here in the middle, generating this resonance stabilized cation. We've only drawn one of the three resonance structures, but we could draw the other two. On the left, we have the reaction with an electron donating group attached to our benzene ring. And we recognize that an electron donating group is going to stabilize the carbocation, either by resonance, induction, or both, but it's going to stabilize that carbocation, lower its energy, and therefore lower the energy of the transition state. So we'll have a lower activation energy for this step than we will for this step. So that shows us why electron-rich benzenes are going to react faster in electrophilic aromatic substitutions than benzene itself. On the other side, we have the energy diagram for the first step of electrophilic aromatic substitution with an electron withdrawing group attached to our benzene ring. This carbocation is going to be higher in energy than the carbocation derived from benzene. Right? This electron withdrawing group, if you withdraw electrons from a carbocation, that's going to destabilize. That's going to make the energy shoot way up. So we have a higher energy carbocation, therefore a higher energy transition state, higher energy of activation, slower reaction than with benzene itself. Okay? So this diagram here, this is one of those pictures that's worth 1,000 words, if not more, because it explains why electron donating groups are activators and electron withdrawing groups are deactivators. Any questions? Okay, so now that we understand the activating and deactivating effects, we now need to understand the directing effects. Okay? And to understand the directing effects, we need to look at the three possible carbocations that one could obtain from electrophilic aromatic substitution at the ortho, the meta, and the para positions. And we need to compare those carbocations. We've already established that the reaction that generates the more stable carbocation will proceed faster. So if we can compare the carbocations from ortho, meta, and para attack or substitution, and we compare their stabilities, we can figure out which one will be formed faster and which one will be the major product. So let's look at an alkyl group first. Let's start with toluene. So we're going to perform electrophilic aromatic substitution of toluene. And we're going to start with attack at the ortho carbon. And we're just going to use E+ as a generic electrophile. So our pi electrons attack our electrophile. We're putting that electrophile ortho to the methyl group. That puts the positive charge meta. And now we have two resonance structures that we're going to draw. We're going to be drawing dozens of resonance structures for the remainder of class, so you'll get lots of practice. Okay, we have one more that we can draw of this particular carbocation. And as we're drawing this, remember there's only one carbocation. It's just a resonance stabilized carbocation that has that positive charge shared by three different carbons. Okay? So as we look at these resonance structures from the carbocation derived by substitution at the ortho carbon, is one of those resonance structures more stable or lower in energy than the others? Okay, which one? The one on the right. Why? It's tertiary. So one of our three resonance structures is a tertiary carbocation, lower in energy than secondary carbocations. Okay? So I'm going to put a box around that tertiary carbocation. Let's compare this carbocation from ortho substitution to the carbocation we would get if our substituent attached at the meta carbon. Okay? We're going to start out the same way, pi electrons attacking our electrophile, but this time we're going to draw our electrophile at the meta position. Okay? So our positive charge is now at the ortho position. And we're going to move the electrons around the ring, showing the delocalization of those electrons as we draw our other resonance structures. Okay? Are any of these resonance structures tertiary carbocations? They are not. When our substituent attaches at the metacarbon, the positive charge skips over the position where we have the substituent, so we don't end up with any resonance structures with a tertiary carbocation. So which of these carbocations is lower in energy? Ortho or meta? Ortho is lower because one of its resonance structures has a tertiary carbocation. Let's look at para. We'll draw that here. Okay, our positive charge ends up over here on the metacarbon. And as we draw the next resonance structure, we find that we do indeed get a tertiary carbocation. I'll go ahead and put a box around that. And then we'll draw the third one, which is another secondary carbocation. Okay? So we find that if we attach our substituent at the paracarbon, we also end up with a tertiary carbocation as a resonance structure. So that tells us that the carbocations derived from attack at the ortho or paracarbons are going to be comparable in energy and lower in energy than the carbocation that we get from attack at the metacarbon. So these products will be formed faster. That's why ortho and para products dominate when we perform electrophilic aromatic substitution on toluene or on any other alkyl substituted species. Okay? Any questions? Okay. Let's look at what happens with another type of substituent. Here is one with a lone pair. Let's look at aniline. Okay, electrophilic aromatic substitution of aniline. And we're going to do ortho again to start out. Pi electrons attack our electrophile. We're going to put the electrophile on the ortho carbon. Positive charge ends up meta. Now we're going to draw our resonance structures. Okay, one more. Is this it, or do we have an opportunity to draw another resonance structure? Okay, anyone want to raise their hand and explain how we could draw another resonance structure in this case? Yes, Grace?
The lone pair on nitrogen control double bond to the
Okay, we've ended up with an atom bearing a lone pair adjacent to a positively charged atom. And our rules of resonance tell us that that allows us to draw another resonance structure, a fourth resonance structure in this case, where we have a double bond between those two atoms. Okay? So that's going to put our positive charge on the nitrogen. Okay? So now we have an additional resonance structure than we did in the previous example. Is there a major contributor out of these 4 resonance structures? And if so, why?
The carbon.
Okay. Why would this be our major contributor?
Octet is fulfilled.
Yes, all of the atoms in this resonance structure have the octet, whereas in these 3, with the positive charge on the carbon, they do not. So we get an extra resonance structure. Not only is it an extra resonance structure, it is a more stable resonance structure because all the atoms have the octet. Okay? Now let's see what happens when we attack at the meta-carbon. You can probably guess what will happen based on what we did in our previous example, but we'll go ahead and draw it out. Okay. So our substituent is going meta. Positive charge is here on ortho. Now we start drawing our curved arrows, moving our positive charge around the ring. And what we find is that when we attack at the meta-carbon, the positive charge skips the carbon that bears our NH2 group, so we do not have the ability to draw that 4th resonance structure. So if we compare these 2 carbocations, the carbocation derived from attack at the orthocarbon is going to be more stable, lower in energy, than the carbocation derived from attack at the metacarbon. Okay? In the interest of time, we're not going to draw the attack at the paracarbon. You can do that on your own. Suffice it to say, it will be comparable to attack at the orthocarbon and will allow us to draw this extra resonance structure. Okay? So this is what happens with amines. This is why amines are orthoparadirectors. And because they're donating groups, they are activators. We could draw similar resonance structures with a halogen, and we would see that the halogens are orthoparadirectors, but they're going to be deactivators because of the net withdrawing effect. You can draw these extra resonance structures, so they're orthoparadirectors, but you have the net withdrawing effect, so they're going to be over here in this area, over here in this area where the carbocation and the transition state are higher in energy. Any questions about this? Okay, last example we'll do is our substituents with a positive or partial positive charge attached to the ring. And we'll do the nitro group. Electrophilic aromatic substitution of nitrobenzene. We'll do attack at the ortho position first. Oops. There's the positive charge at the metacarbon. Now we're going to delocalize that using our curved arrows. Okay. Okay. And here I'm going to go ahead and draw out the Lewis structure for our nitro group. Okay. As we look at these 3 resonance structures, do you notice anything about any of them that would make it less stable or higher in energy than the others? Yes? Yeah, if we look over here at the structure on the right, we have 2 atoms with positive charges attached to each other. That's going to be highly destabilizing. Of course, this carbocation is elevated in energy because we know that the nitro group withdraws electrons from the benzene ring. But this is going to be particularly bad in terms of a resonance structure because we have two atoms with positive charges attached to each other. So that positive charge is shared by an atom that is attached to a positively charged atom. So that is a particularly bad or unstable situation. Let's see what happens when we attack at the meta position. Okay, so we end up with the charge ortho. We start to delocalize the electrons. Okay. And what we find is that when our new substituent attaches at a metacarbon, that the positive charge skips over the carbon that bears the nitro group. Okay? So inductively, that nitro group is still withdrawing electrons. This carbocation is higher in energy than the carbocation derived from attack of benzene itself, but it's not as high in energy as the carbocation derived from attack of the orthocarbon, because the orthocarbon carbocation has this really bad high energy resonance structure. And if we were to draw attack at the paracarbon, we would find the same scenario as with ortho, where we would end up with one resonance structure with positive charges on adjacent atoms. So drawing the resonance structures of all the carbocations that are possible from attack at the ortho, meta, and para positions and comparing them will allow us to understand our directing effects of substituents. Any questions? Yes?
I'm just going to ask on that ortho substitution, would that ever be strong enough to knock off the nitro group?
You mean to have the nitro group as a leaving group?
Yeah, because of the two like charges.
Okay. No, your nitro group is not going to be a leaving group in electrophilic aromatic substitution. So yeah, you might think, okay, there's enough repulsion, you're going to break that bond. Not enough repulsion for that. That sigma bond is too strong for that. Okay. So a reminder, this is our table here. You shouldn't memorize the information in the table. You should be able to look at any of these substituents and understand why they appear in the region of the table they do, using the reasoning we went through today. All right? We'll see you on Friday. Make sure